Yesterday we were discussing the different types of solidification modes in your weld metal. We studied that there are different types of solidification modes such as planar solidification mode, cellular dendritic, columnar dendritic, and aqueous dendritic. As you can see from this diagram, basically there are three commonly observed solidification modes: cellular dendritic, or columnar dendritic. However, it is very difficult to obtain the planar solidification mode as well as the aqueous dendritic mode. As in aqueous dendritic growth, this is not normally observed in fusion weld due to large constitutional supercooling required during the solidification stage. These are the points which I have discussed in the solidification of our weld metal. Then after this, we will discuss what is happening in the region near the fusion boundary or near the welded section. You know that, as you can observe from this figure, this is a welded part and basically it is represented the weldment. So in the center you have deposited your weld metal, and you have seen either the columnar or columnar dendritic type of microstructure. And then the second zone is the weld. In the weld joint is the weld interface, where you have partially melted grains of your base metal. Okay, in this region you can see that the region close to this weld interface, here the actual bonding takes place in the welding. Now you have deposited the weld metal and then solidification has started. So whatever heat supplied in the middle section, it will migrate towards the base metal side. So this will be the direction of the conduction of your heat. Some of the base metal which is near to the weld metal, it becomes heated, and certain microstructural observations will also observed here, and such microstructural observations are due to the interaction of the heat with the base metal, and such area where the microstructural transformation has occurred but there the melting is not occurred, so that particular region is known as the heat affected zone. This heat affected zone is further divided into three zones. So the first zone is the coarse grain heat affected zone, and the second zone is the fine grain heat affected zone, and third region is the intercritical or transition zone. The first region is very close to the weld metal zone. If you can see from this diagram, they have mapped this iron carbon diagram, means they have considered a case of welding of suppose this 0.15% carbon steel, plain carbon steel. They have observed and correlated with the microstructural transformation with the iron carbon diagram. So if you can understand that this particular region has been heated above the upper critical temperature. So this line, this 727 degrees centigrade, is the lower critical temperature line, and this which is denoted by A1, and then this line is your A3 line, which is the upper critical temperature denoted by the A3 line. If you can observe that this coarse grain region is well heated and most of the heating has commenced more than 1148 degrees centigrade, the maximum temperature has reached up to 1500 degrees centigrade. The region where the heating has been done and the temperature is in the range of 15 to 1200 degrees centigrade, so that particular region is your coarse grain structure, and the grain coarsening is observed in this case. And below this means it is just above the A3 line, and means this 912 degrees centigrade, or depending upon the composition or the carbon percentage, this is the A3 line. If the base metal is heated up just above this A3 line but below this 1148 degrees centigrade, that particular zone is your fine grain heat affected zone. If you also know that this is the region of your recrystallization in your iron carbon diagram, and if you remember in your metallurgy class, the faculty might have explained you about this, that this particular region which is just above this A3 line is recrystallized, and you will have fine grain microstructure. So this particular region is your fine grain heat affected zone. And after this there is a transition zone which is adjacent to the grain refinement zone. Here the metal is heated to a temperature between the upper critical temperature line and this is the lower critical temperature line. So this particular region is your transition zone. In this zone the grains are somewhat bigger than the fine grain heat affected zone but smaller than the grains of the base metal. If you remember that there are three terms in this particular section, which is the recovery, then second is the session, and third is the grain growth phase. So in recovery phase, if you remember, this recovery is happening because if you apply heat to the dislocation inside these grains, they rearrange themselves and they produce a strain-free region. So that strain-free region is what is giving the sites for the nucleation of small grains. So this is the region where the recovery starts, and then if you continue to supply the heat, then this nucleation starts to form, and the new grains will start consuming the old grains, and then it will achieve the grain refinement in this particular range, which is in between the upper critical temperature line but lesser than the 1148 degrees centigrade. This is the recovery zone, recrystallization zone, and then if you continue to heat up your grains, the grains which are very closer to each other, they will start to diffuse into each other and form a coarse grain like microstructure. If you heat above 1500 degrees centigrade, then you will observe the metal or the grains will be melted again, and you will reach the fusion zone or the liquid state. So this is the region of heat affected zone, and why you are getting the fine grain structure. In the region of fine grain heat affected zone, you have a recrystallization, whereas in case of coarse grain heat affected zone, what is happening, there is a grain coarsening, and in the intercritical zone, the enucleation is just started due to the rearrangement of the dislocation inside the grains. The region outside this heat affected zone is your unaffected parent material, and here the grain size is unchanged and will be same as came in the procurement condition. Whatever initial treatment happened on the base metal, the grains are not going to change because here the heat has not reached and have not changed the grain size of the base metal. So this is the whole interaction of the base metal to be joined with the heat. In the first step, we perform the welding process under different metal transfer modes. We have supplied the weld metal into the welded section, and in the welded section the grain starts to nucleate at the surface of your base metal. The partially melted grains at the surface of the base metal, they will provide the site for the nucleation, and then grains will start to form with the different types of solidification modes depending upon the temperature gradient and the solidification rate. Basically the cooling rate, you have different types of solidification mode. Planar type of solidification, it may be cellular, it can be cellular dendritic or columnar dendritic, and then the aqueous dendritic. You know that how you can achieve the dendritic mode, different types of mode, that depends upon the different regimes of GR, means the cooling rate, and the temperature gradient and the solidification rate. And then after the solidification, so that the heat will migrate towards the base metal, it will heat up the certain region of the base metal, which causes the region microstructural transformation, and this particular region is known as the heat affected zone. This heat affected zone is further divided into three different regions. One is the grain growth region. This region is very close to the weld metal zone. Here the metal is heated well above the upper critical temperature limit, and it results in the grain coarsening and the grain growth. And then after that there is a grain refinement zone. Here the recrystallization occurs, and it is near to the grain growth zone, but here the metal is heated just above the upper critical temperature, and it results in the finest grain structure. Then after that there is a transition zone which is in the immediate vicinity to the grain refinement zone. Here the metal is heated between the upper critical temperature range and the lower critical temperature line. These are the three zones of the heat affected zone. All these zones or the microstructural transformations are occurring due to the recovery, in which the nucleation happens due to the rearrangement of the dislocations to produce the strain free regions, and those strain free regions inside the grain will give a site for the nucleation. And then if you continue to heat up the grain, then there will be a recovery of the new grains, and new grains will start to consume the old grains. If you continue to heat up the again, then all these recrystallized grain will try to diffuse themselves and form a big grain. After that, the region outside the heat affected zone is of the parent metal, where the grain size is unchanged. So this is all about the interaction of the heat with the base metal, which results in the different microstructural transformation and formation in different regions of a welded structure. So, if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.